All right. So today we are completing our intro to full stack journey, and we're going to see how to write JavaScript that we can now run in our browser to talk to a server. And so for this part one, we're going to talk a little bit about what's an IP address. Um, we're then going to learn about the different protocols about how information is sent over the internet with the Internet Protocol, Transfer Control Protocol, and our friend, the Hypertext Transfer Protocol. We'll talk a little bit more about HTTP requests and really look at the anatomy of an HTTP request and response. And we'll also spend a little time looking at cookies. Part two, we'll actually get hands-on with our JavaScript and use it to talk to a server and have our JavaScript then take that data we grabbed from the server and display it in the browser, thus completing the full stack loop. So hopefully exciting stuff. So let's talk about IP addresses. We've talked a little bit about computers and ports, and if I hop over to some of our diagrams, and actually let me just briefly say sort of what our goals here are for today. As mentioned here, this is not just about the hard technical skills of how to build this, but we're going to be learning some of the fundamental concepts of how programs communicate across the internet. We're not going to quite dive into networking, but we're going to start learning a little bit of those things. So these are really core concepts that are at the foundation of modern software development and networking and computers and everything. And so this stuff is really important for building web applications. And as time goes on, your knowledge will keep expanding in this area. So IP addresses, and let me kind of navigate through our many diagrams that we've developed over the last several weeks to get to one of our favorites, which is about ports. And we've talked about how my computer is really running a little network and has its own IP address. And I can have different programs on here running that have different ports. And it's sort of like different addresses for different apartments in an apartment building. Um, we also talked about how different computers can talk over a network. And so the same way that my machine has all these different addresses, and forgive me, let's grab the whole diagram. When we're talking about the internet or any other network, as we navigate here through the world of TLDraw, we're talking about the same thing on a larger scale. And in a lot of ways, we can really think of the internet as one big machine. And instead of ports with individual programs running, this network, right, that we call the internet, is a whole bunch of different computers, whether it's a physical server in a data center or a virtual server running on a physical server in a data center. And they all talk using the internet protocol. And there's more steps involved in this. There's things with routing and other things. But at the end of the day, that's really what we're talking about here. And when we talk about the cloud, in a lot of ways, that's what we're talking about as well. And so maybe we have, instead of port 5500, we have, the PokeyAPI.com. If we go to our friends, PokeyAPI.co. And let's go to the homepage for our Pokey API. And we have here our host name. And if we go to Wikipedia, Wikipedia also has a host name, or a domain name. Those terms often get used interchangeably. And if we go to Amazon that we saw, Amazon has a name as well. And forgive me as I get our tail draw going here. But just the same way I might have names in my phone book on my phone, and then those are related to phone numbers. And so on. It's the same thing with host names or domain names and IP addresses. And in fact, if I hop over to my terminal, there is a command line program called NSLOOKUP. And if we very quickly look at its manual pages, it lets us get information about internet name servers or servers and domain names. And we're not going to have to use NSLOOKUP a ton, but it is great to use to help illustrate how host names and domain names work. When I do this, NSLOOKUP is not talking directly to the Poke API website. It's sort of going to what's called a domain name server or a router, which is some other computer running somewhere on the internet, depending on, if my internet provider is Comcast, or just how things are organized. And those domain name servers kind of pass this message around saying, hey, Adam's computer is looking for Poke API CO until someone who knows what the real IP or internet protocol address is. Right. And in this case, it's 104.21.76.139. Right. And so the same way that I have numbers in my phone book, where I have like the alias or the person's name, I have my host name or domain name and the actual IP address. And so these are what computers really use to talk to each other. And part of what the internet does is it has domain name servers that look these things up for us, but it's the IP addresses where things live. So instead of ports on a computer, we have IP addresses on a network. Right? And I have an extra square here, and let's just make that. We'll just leave that as is because TL Draw seems to want to fight me on it. And again, Amazon has its own IP address. And apologies that this has gotten a little messy. And then somewhere over here is my computer. And then when my browser, when I want to go look at the Poke API site, at the end of the day, though there's some routing and there's some intermediate servers involved, think of it as sort of like the Pony Express or in Lord of the Rings where they're lighting the beacons and the message goes from one to another. There's some intermediate servers along the way, but I can send a request over the internet to the Poke API, and the Poke API sends back data. And that's exactly what's happening here in the browser with this HTTP request. And we've seen a bit of a preview of the network tab and how it's not just one single request. It's a whole series of requests that happen. And in fact, if we, let's see, can we view somewhere in here, we can actually sort of view the history of the requests. There we go. And we can see here, we start out with these requests and we're requesting a whole bunch of different things. And we see that there's actually a whole bunch of communication between my server and, or my browser and the Poke API, right? And it all starts with getting the index.html homepage, which then causes us to load many other things. And all the way down here, we have loaded some sort of JavaScript to do something. And somewhere in here, we see there's more and more JavaScript. Here we see a CSS file that has information about fonts. So all of this information is coming from the Poke API server that my browser is fetching and then rendering. So big picture, that's sort of what we have going on, is these computers communicating over a network with IP addresses. And the next question here is, let's dig into this a little bit to see how this happens. And there's a couple different, what we call protocols. And these are just the rules for how programs will talk to each other. And it's in fact exactly like the rules for driving, right? Drive on, in the United States, the right side of the road. Green means go. Yellow means stop. Or yellow means slow. Red means stop. And then at a stop sign, you know, what is it, clockwise? I can never remember the order of precedence for who gets, to go first. And, pull over to the side for emergency vehicles, right? And there's all sorts of rules, but nothing is actually stopping us from breaking those rules. I mean, if a police car catches us, then we'll get a ticket and we'll get in trouble, right? And in fact, related to that, the rule I think we probably all break the most when driving is the speed limit. And it's the same thing with protocols. Basically, protocols are just a massive agreement by the world of software engineers on how we are going to write our code. And in fact, there are what are called requests for comments by what's called the Internet Engineering Task Force. And this is literally sort of the committee that creates the internet and how it should work. And so everything that we use with the internet, with how HTML works, with HTTP requests, eventually either sort of originated through this, and this sort of came out of US government research and academic research in the 60s, but it's still around and it's sort of like the guiding force. And it's actually kind of really interesting. And then they develop all of these standards. And if we scroll around here, let's find, this looks like a good one, RFC 9791, that defines the internet protocol. Let's see if we can find that one. And if you really want to go deep, you could read these. I really have not, to be honest. But what I want to illustrate here is that there's nothing magic about the idea of protocols that we're going to talk about. It's just like traffic laws and rules of the road, a series of rules that people have created and that everyone agrees to abide by when they write programs. And you can see that these are pretty formal documents, right? And then, as I mentioned, a lot of this started with DARPA, like Defense Advanced Research Projects Agency. The internet was originally designed to be a resilient network that would survive a nuclear war, so people could keep communicating. So a lot of this came out of that, and it was that sort of defense academic partnership. And so these RFCs get created, and the people involved with this then comment on it. And you can see here a motivation and the Internet Protocol, IP. The idea is that we want to transmit small blocks of data from one point to another, and we want to send packets. And I want this to be flexible so that if part of my network goes away, whether it's because someone tripped over a wire or something really bad happened, the network can route these packets and information around. And so I want it to be okay for there to be fragments in my message. I want it to be okay for there to be issues. And if we kind of scroll through this, we can see more and more detail about what the internet protocol should be, right? And the descriptions. And we see it breaks it down even to like all the little details of which bit stores which part of information and where things come through and so on. So when we're talking about communicating over the internet, we actually have several different protocols in action. And the IP protocol or the internet protocol is the base of this. And this is sort of like a protocol stack. And let's make a big diagram here. And let's make it even bigger. And so at the base is the internet protocol, IP. And its job is to handle addressing and routing. It gets data packets from one computer to another across networks. It doesn't care or know what's in that data. It doesn't know about HTML or HTTP or any of that. It doesn't even really care if the message is received. On top of this, and using the internet protocol is another protocol called TCP. And let's make this a bit smaller so we have a bit more room. And this is called the Transfer Control Protocol. And TCP's job is it sits on top of the internet protocol, and I'll talk about what that means in just a moment. And it adds reliability. It ensures data arrives completely and in order. And a simple example might be putting start at the beginning of a message and end at the end, so we know if we got the whole message, right? As opposed to if you've ever maybe gotten a text or like in a chat, like you're not sure if someone wrote the whole message or not, or if they were done, or if someone was finished speaking. And so what happens is I can write a Python program to convert some data into this TCP protocol format and send it the way that other programs using TCP expect it to be. And then I have a program that will convert that data in the TCP format into the IP format. And so that's what we mean by sitting on top of another, right? So I might transform some information to this TCP protocol standard, but then it gets transformed again into the internet protocol. And that's how it's actually sent across the wire, across the network, so to speak. And then finally, on top of this, we have our best friend, the HTTP protocol. And hypertext here is an older term. Um, it originated when all of this was much newer, and the idea of having text where you could click on a link or you could see images was really exciting. And so someone decided to use the word hyper to sort of try and indicate that it's not just sort of static dead text in a book, but it's got some interactivity to it. And now obviously it's expanded way beyond that, but that's where the term comes from. And it's gone way beyond this because this really is the protocol that determines how clients and servers, so for example, browsers and servers, communicate. And this is the format of what we call HTTP requests and responses, which we've been talking about and we see in the network tab that really define how things talk over the internet. If I'm playing a multiplayer game and I've got, I don't know, Counter-Strike or League of Legends running on my computer, so much of that data might not be sent using the HTTP protocol. It might be using TCP, and then that's getting converted into IP. But whenever we're using a browser, and 90% of the time when we're talking about web applications, we're sending data back and forth using HTTP. And just like TCP gets converted into IP, an HTTP message gets converted into TCP. And the cool thing about HTTP is that it is user-friendly, relatively speaking, to read. It's by design in a plain text, human readable format, and we're going to take a look at what that format looks like in just a minute. And in fact, let's use my favorite tool, curl, and get a quick helper on how to do this. There we go. So if I go to the command line and I use this command line program, curl, that will send an HTTP request over the internet. We see all this stuff. We'll break this down more simply later, but if I scroll all the way up to the top, and here we go. We'll see this more nicely in a slide deck in just a minute, and we can kind of ignore all these brackets on the side. But what I'm kind of highlighting here is an actual HTTP request message. It's plain text, and we say what kind of action we want to perform. We send a host name. We say what kind of program the client is, or the program acting behalf on the user, acting for the user agent. So when I'm using a browser, this would say Chrome. And this indicates the kind of file formats we can accept and return, which is everything. And here we see the HTTP response. We see the date. We see the kind of content that's coming back. So this program knows how to format it, the character encoding, cache control, something about age, a whole bunch of what are called response headers that we'll learn about later. And then if I start scrolling down far enough, we see what's called the body of the response. And this is not very nicely formatted, but we can see that we have, in fact, an HTML file in plain text. And you guys have seen me show this in the network tab in the browser. And this is sort of a plain text version of that. And I just wanted to do this to kind of emphasize that the HTTP protocol really is just human readable text, though obviously it's pretty dense. but at the end of the day, it's human readable text. And in fact, it is the job of software that we don't have to write for ourselves to turn this human readable text in this HTTP format into the TCP format or protocol that gets turned into the IP format, and then that is actually, sent over the internet from one computer to another, right? And then that information is reformatted back. And this all happens at sort of layers of the program below what we have to deal with. And we sort of get to stand on the shoulders of giants here. So let me go ahead and pull up a slide deck that we have that breaks this down a bit. Um, and before I do that, I just want to pause and see what questions folks have or what people are curious about. And how are we doing thus far? Because I know I've been doing a lot of talking, so I just want to check in. Um, Alex, yes, sir.
What are some examples of people breaking the rules, these protocols, and the repercussions?
Yeah, that's a great question. Um, it's pretty simple since pretty much all the programs on the internet work this way. If I want to try and talk to another computer over the internet and I don't follow these rules, I won't be able to send a message successfully. And that's really it. Rick, yes, sir.
Yeah, maybe it's just because I'm not used to maybe we're somewhere else in the model. But uh what part of the model are we actually in? Are we in like the application layer or because like I'm used to like seeing like ICMP in there and stuff like that.
Yeah, that's a good question. I actually am not sure what ICMP is. Um,
That's it's mostly for like maintenance, like ping, that kind of thing. Like ping goes
got it.
over ICMP.
Okay. Yeah, that's going to be pretty low in the protocol stack. My guess is it's somewhere around here. Let me look it up because I always get the I know exactly what you're talking about, and I always get the terminology wrong. Um, and let's see if we can find a nice diagram.
Yeah, because I'm used to seeing like it depends like if we're talking about H HTTP or if we're talking about the entire thing because you have the application layer which is where all what creates or generates the data, then you got the transport layer which is your UDP and your TCP, and then you got the internet layer which is like
Right,
your IPv4, that's where your ICMP and your
right,
ARP reside, and then you got your network. So, all right.
right. And yeah, and to jump in, we're really staying up here at the application layer. Oh, excuse me.
Okay, cool. Yeah, I was just trying to figure out where we were in the layer. All right, thanks.
Yeah, definitely. You touch on a good point. This idea of sort of like layers of an application goes deeper, especially when we get into like networking software and the physical layer of how do I turn something into actual electrical signals. The beauty of software and this idea of abstraction is I really don't have to worry about the lower layers. And so we've kind of covered, maybe it's over here in inter-host communication. As I said, this is a bit of a deeper well, and I really just want to kind of introduce some of these fundamental concepts. But for the entirety of this course, we are really going to be focused on HTTP because all of the applications that we write really only need to deal with HTTP.
Yeah, like you said, shoulders of giants. Everybody else
Yeah,
did this for us.
yeah, exactly. And it is valuable and important to go deeper and learn about that stuff, but this is sort of like where we're going to have that entry point into it.
Yep. All
So
right,
with
cool.
thank you. With HTTP, hypertext transfer protocol, designed several decades ago. We've kind of seen it in action. As I mentioned, it supports a lot more than just text, and we use it for all sorts of things. You could design a real-time chat app to use HTTP. There are other protocols you could use as well. You could, in fact, make a multiplayer game that sends data back and forth using HTTP. And sometimes that's a bad idea. But if it's like chess or backgammon or something that doesn't need like massive amounts of streaming real-time information, maybe it's actually a good idea because this protocol is so popular and there's so much that supports it and it's become so easy to use. So HTTP is used to describe a conversation between two computers, or two programs rather. One we call a client and one we call a server, right? And a client could be a browser. It could be that curl command line program. It could be a browser on a phone. It could be my JavaScript code running from the command line. So a client can really be anything. And a server is also just a name for another program that receives information from a client. So a server could be my Python Flask program. It could be a JavaScript program running with Node.js. Usually when we're talking about a server, we're often talking about a program running on another computer. So it could be, running on another physical machine, maybe in a data center. But it could even be a virtual machine that's not an actual computer. We can even have the client and the server on the same computer, which is what we've been doing in class, right? When I have my browser talk to my Flask program, I have the client and the server running on the same computer. But when I am using my browser to talk to the Poke API, the client and the server are not different computers, but they're connected over a network. And that's the beauty of networking and protocols is I can use the same protocol and the same approach regardless of where those things live. And apologies there, I jumped ahead a little bit. The client sends a request and the server sends a response. And we saw a preview of this with curl, but let's break this down a bit and look at what we have here. The first part of the request is what we call a verb that is telling the server the kind of action I'm going to perform. Am I going to get information, or am I going to send or post you information, or am I going to want to delete information? This is called the universal resource indicator, I think, the URI. You can think of it as the path to a file or a resource. Sometimes it's an actual file. Sometimes in the case of, say, the Poke API, it's not an actual file, but it's sort of like a path or a series of rules telling the server what I want, that I want a Pokemon with the ID of 1, right? Or maybe I want to see all the moves that that Pokemon has. So this URI we call a resource because sometimes it's pointing to a file, but sometimes it's telling the server what information I want. And we'll learn more about that later with REST APIs. And here we're telling the server what protocol and what version of the protocol we're using, information about where we are coming from, our host, and what kind of program we're sending from. The server sends back what's called a response code, and we'll dig into those in a second, that indicate success or failure or other things. A human-friendly message. The server also tells the client like what protocol it's using. It tells the client how much information it's sending back, the date, and it tells the client how the information it's sending back is organized. And then here is what we call the body of the response, which is where we see, say, the text of an HTML file or of a JavaScript file or JSON. Right, and so to kind of just step through this again and break this down, we have the HTTP method or verb, the URI, and the protocol version. There are several different HTTP verbs. When we get deeper into the course, we will be using these other ones. And this is, again, sort of convention. It's rules of the road that have been evolved so that if everyone follows them, it's easy to communicate. So if I'm entering my username and my information when I'm creating an account on a website, and then I submit that information to Amazon.com when I'm signing up, that's an HTTP post request because I am telling the server I wanted to create a new user account. If I wanted to, say, modify my username, that would be what's called a put request. If I wanted to delete a student from a database, that's a delete request. And then the get and retrieving a resource is what we do all the time when we get websites or information about students and so on. Alex, yes, sir.
Is this somewhat similar to like a CRUD app?
Exactly. A CRUD app is just a less formal way of referring to this, where CRUD stands for create, read, update, delete. And it's the exact same thing, right? It's just that over here, we're talking about the language of HTTP and how we use HTTP requests to do these different things. And so what we'll end up doing is our client will maybe, excuse me, make a post request to create some data. And in our Flask code, we will write some code to talk to a database to do that. And just kind of moving through this, we have the uniform resource identifier, right, which is very similar to a URL, a uniform resource locator. And we see the structure of an HTTP request here. As time goes on, we will see more headers for different things, but these are sort of the most fundamental and important headers. And if I was sending information, it would be here in the body. Right now, I wouldn't need to, but if I wanted to, say, create a user account, I might put some JSON in the body of my email that was being sent, or the body of my HTTP request. Excuse me. And here we see an example of an HTTP request with a body. And in fact, this HTTP request is doing something really interesting. It's searching. So if I'm typing in the Amazon search bar and I hit enter, it might construct an HTTP request sort of like this. And here in the body of the request, we see some information where I'm searching for some sneakers, right? Some red Jordans. You normally see request bodies when we're creating or modifying information. You can put all sorts of data in here. You can put an image in there. You can put binary in there. You can put form data. You can put anything, but you do see it sometimes used like this for searching. What is a more common way to see searching, and this probably looks familiar if you all sort of go through your memory and think about the different URLs you've seen over the years in the browser's address bar, right? We'll kind of ignore this part about the protocol and let's just focus on the URL. There's a question mark right here. And so everything after this question mark is called a query string. And so here I have in the actual URL that's typed into the browser, the information about what I want to search. And we see it down here as well. And so then Amazon server, when it gets this HTTP request, is going to be looking at this URL, and we're going to use some code to break this down, right, to get the value of what they're searching for and other information. And when you do this, everything after the question mark, it's called query parameters. And you see here, it's a key, an equal sign, right, and a value with some character encoding. And when you have separate query parameters, they're separated by this ampersand, right? So I have two query parameters here. I have this one, and then this one. So you might end up embedding a whole bunch of things in a query string. You could have like 5 or 6 different query parameters. And we'll see this in action as we get deeper into the course. Headers provide lots of additional information, and both requests and responses have headers. So the host tells the web server the domain that the client request is coming from. And this is especially useful if my message needs to pass on through multiple things. And it's like if I send a letter in the mail, I put in a return address on it because it goes through the post office and it gets delivered by a mailman. And that way the person who received it knows where the letter originally came from. We can use a request header to say the language that the user wants. We use a request header to tell the server what kind of program, what kind of client sent this request. This could matter for things like dealing with showing websites differently on mobile phone, on phones versus desktops or other things. And then what format the client wants data to come back in, right? And text/HTML, text/plain or comment, and you'll also see JSON and other things as well. An HTTP response follows a really similar structure, right? We have the status line, we have the response code, which I'll talk about in a minute, indicating if things succeeded or not, a message that goes along with the response code, how much data comes back, the date, the format the data is in, and then the body of the message, if there is a body in the response. So this just breaks down that response status line, and the status code is probably the most important bit there, and we'll talk about that in just a sec. So with status codes, there's a bunch of, standardized status codes. A 200 response code means the client's request succeeded. I was able to send you back information about a Pokemon, and I'll demo these in just a minute. Sometimes we get what's called a redirect. If you've ever gone to a website and been redirected to another, that's the server sending back a 302 response with the URL of where the browser should request to. If somehow I've screwed up and made a bad request, like maybe I'm searching for a Pokemon that doesn't exist, I should see a 400 response, and I'll demo that in just a minute. If I'm not logged in or not allowed to say access the admin site of a website, I might get a 401 unauthorized response. The 404, is actually the response for if something doesn't exist. This means something was, I made a mistake. Maybe I formatted something wrong. The 404 means the data doesn't exist. And then finally, the 500 internal server error means server made a mistake. Maybe something is broken on the server side or something went wrong on their end. And just to demo these real quickly, let's see if we can't show a couple of these in action. And I just need to get rid of my annotation. So let's go to our friend, the Poke API, and let's open up the network tab. And I know that I can search for a Pokemon like this, right? Let's search for Ditto. Let's copy that to the clipboard. Let's put that there. And if I do that, I scroll all the way up to the very first request, and we look at the request and the response. And let me give us a little more space here. Now that we know what we're looking at, we see that this is just sort of a nicer interface to see the plain text HTTP request and response. And this just shows the body of the response. But over here, we see the different response headers. Somewhere in here is, in fact, the 200 response code. They may not be showing it to us here in DevTools, though it's definitely hiding in here somewhere.
No, it was at the top. It has a green marker next to it. Yeah,
Oh, thank
status
you
code.
so much. Yeah, they call it status code. Awesome.
Yeah,
Thank you. Yeah. So let's say we try to search for a Pokemon that doesn't exist.
Huh? Huh?
So we see this simple not found message, but now if I go look at my HTTP response here in the browser, though I worry it may, there we go. We see status code 404 not found. All right. And so again, it's these rules of the road. And the Mozilla Developer Network site, again, is sort of the best standard for looking up these things. And you can see there's actually a whole bunch of different responses. And these were, again, defined by an RFC from the Internet Engineering Task Force. And there's a couple fun ones in here. There's some older ones. Somewhere in here is actually, here we go. I think this was from an April Fool's RFC, but the server can send back a 418 I'm a teapot response. On a practical level, I think that's used to make sure that the server exists. And so clients and servers are using these protocols and sending these messages back and forth all the time to communicate. Right? And we have a client and we have a server. And there's a couple extra steps. You'll see, I believe it's a 203 status code. Before a lot of requests, the client sends an HTTP request to see if the server is available. Or sometimes, like, it might be a request saying, do I have permission to do this? It's called I think it's called an options request. And then the server sends back a response saying basically yes or no. And then the client might send its actual request. And so maybe what we want to do is we want to get the student with ID 3, and then the server sends back that data. And in the body of the response is JSON text in the JavaScript object notation format with information about our student. And this is happening all the time, right? Because it's not just this, it's for HTML pages, it's for CSS files, it's for JavaScript files, it's for image files, it's for everything. And there's a little bit more here to cover, and then we'll take a break. The response headers are pretty similar to request headers. As I mentioned, there's a whole lot of back and forth that happens for an HTTP conversation. And then most importantly, with HTTP protocol, it's designed to be what we call stateless. So whenever I'm sending a message, it has to have all the information that I need. The server is not really storing information or tracking if a conversation begins or ends. And this goes back to the idea of the internet being a flexible network where if parts of it are down or delayed, communication can still occur. So again, if I'm playing a multiplayer game, then they might not be using the HTTP protocol. Now, servers, obviously you can log in, right? And log out. So sometimes what happens is while the information might be being sent with this stateless HTTP protocol, on top of it, the server is, creating what's called a session. So just because the information is being sort of passed back and forth statelessly doesn't necessarily mean that we're unable to have like sessions or users logging in or logging out and stuff like that. And I see a couple questions, and give me just a minute to walk through this a bit more, and then we'll pause for questions. So there are some ways to get around this. And the most common one is called a cookie. And to illustrate this, let's go back to our TL draw diagram. And let's say that we have, excuse me, a different scenario. Let me go ahead and just copy this, and we'll drag this over here. And the dictionary just wants to show up because it's tied to some sort of keyboard shortcut. And let's say that, and there it is for hopefully the final time. Let's say that instead of getting information about a student, I want to log in. And when I'm doing this, this would be encrypted, but I would pass my username and my password. When the server sends back this response data, and maybe it's sending back like user profile info, it also sends back what we call and let's make this blue. There we go. It also sends back what we call a cookie. And the cookie might be, say, what we call an auth or authentication token. And it might look something like this and basically have some hashed or encrypted information. And somewhere where the server is talking to the database. Okay, I don't know if you guys heard that Bob Dylan music pop up, but I had apparently the music program was running on my computer and I did not realize it. So I might have a database over here, and I apologize. I don't know why I'm having such a hard time with the dictionary today. There's some Mac mouse shortcut where if I press too hard on the touch bar, it comes up. So I'll have to get rid of that. But in our database, we might have a table, and that table might be user login. And when I perform this login operation, somewhere in the database, this is stored. And so now this cookie, this is sort of passed under the hood. I can't use my JavaScript code to interact with this directly. I can view it, and that's why it's encrypted, and I'll show what a cookie looks like in a second. But even though this sort of authentication cookie has been sent, I still, as the browser, have to send it every time I want to do stuff. And the browser will actually do this automatically. So maybe, I'm getting, if I want to look at my user profile, when I send that request to the server, I have to include the cookie. And that's how the server authenticates that this request is coming from a user who has permission to do this. And in that sense, this is stateless, right? Every time I make a request to do something like this, I have to make this request. Like maybe it's not, user profile, maybe it's also my favorite Pokemon, something tied to my account. I have to pass this cookie every single time. And in fact, if we go to the Amazon website and I go here in the network tab to application, and we look down here, we can see there's all these different cookies in the browser. Sometimes they're used for logging in. Sometimes they're used to track people. So this is how one way for Amazon to know that me, Adam, is going on the Amazon website. Sometimes it's for session information. Sometimes it's for preferences. This is, I believe, indicating I like to see prices in US currency. If I'm logged in, say to GitHub, note how the browser only shows me the cookies for the site I'm currently logged into. And we see here a user session cookie that has some sort of encrypted information about device ID, keeping track of whether I prefer light mode or dark mode, my username, and if I'm logged in or not. So all of this is stored on the browser, and then a lot of this is automatically sent from the browser to the server on every single request. And so when we're talking about stateless, that's really what we mean. We're going to learn more about cookies later, but the idea here with a stateless protocol is that every time I send a request, I need to pass along all the information the server needs. So if I've logged in, I need to pass in through a cookie or another means like my authentication token or whatever it may be. For other things like say streaming video, it might be using a different protocol, but with HTTP, it's a stateless request. We can still build sessions and logging in and stuff on top of that. But under the hood, the HTTP protocol is stateless. So let me just pause here and see what questions folks have. I know there are a couple hands and we covered a lot of ground. So I think this is a good time to pause for questions and then we'll take a break. Rick, yes, sir.
Oh, sorry, I was trying to get the mic. The first question is the when you were going over the returns, the responses. Whenever I was doing the project yesterday, I noticed that I was getting 203 a lot. Well, all the time.
Yeah.
Is that have to do with we were changing things with JavaScript? Is that why we were getting like the 203?
Yeah, great question. The 203 is basically the client saying, can I talk to you right now? Do I have permission to do this? And the server saying yes or no. Because, for example, if I'm about to download a big file, but I don't have permission to do it, rather than try to download the big file and have a bunch of back and forth that wastes bandwidth and stuff, the client sort of asks for permission first. And so it gets, the description here is a little tricky, but I think it gets used essentially in that way. And that's why you'll see like a 203 before a lot of other responses.
And
Yeah,
then
great
last question, just real quick. I haven't looked it up, but is the cookies is that why a lot of users complain about a lot of cookies cached to their their browsers causes the browser to slow down because
It
it's trying to process all those cookies, or
it
it's
can
probably
it can be other things as well. The browser caches, you touch on a really good point. The browser caches a lot of information as well. It can cache whole JavaScript files and stuff like that. So clearing the cache to speed up the browser gets rid of a bunch of other stuff other than cookies. Clearing cookies is usually more for like user tracking or if I want to kind of like refresh how a website behaves. Yeah, great question, man. Alex, I think you had a question as well.
Yeah, you sort of answered it with the sessions, but since HTTP is stateless, why does it send a date in the response?
Yeah, that's a great question. So state would mean more like once I've logged in for all my future requests, I already have permission to do whatever I want. So, for example, in a stateful protocol, once I have logged in, I wouldn't need to pass this authentication token every time. I could just make requests the normal way and I don't have to prove who I am. Right? It's it feels stateless because I only have to type my username and password once to log in. But the way to think about it is that under the hood, I'm effectively typing in my username and password every time I'm interacting with the server. It's just that what the server does is send me an auth token and the browser sends that every time. A stateful protocol would be I type in my username and password once, but then I can just keep communicating. So things like dates, it's not that kind of state, if that makes sense, right? Because the date is the date and it isn't affected by whether I've logged in or not, or like when I started my session. Tom, yes, sir.
Is that where we get the, I mean, obviously the acronym stands for something different, but is that why we call them like RESTful APIs? Is because like they're not constantly like pinging for communication and info in this manner, so they're kind of stateless.
It's a good question. REST stands for something else.
Right.
Yeah, no, it's a RESTful API indeed is stateless, but that doesn't have anything to do with the name, though the REST API is also kind of designed to work this way as well. REST stands for, man, this is going to be fun. This is going to be a mouthful. Let me find the Wikipedia page.
I was just wondering because I know that programmers often choose very nerdy and interesting
Yeah,
naming conventions. So I
yeah,
figured even though it's not necessarily the same thing, it might tie in a weird roundabout
yeah.
kind of way.
That would have been cool. I don't think the guy had it in mind when he did it, but I never thought about that, and I like that because that is a clever way to talk about it. That the API is restful. It's resting because it's stateless. But no, I think he just took this mouthful right here of representing a transfer of state and then turned it into an acronym. Yeah, good question. And we've already started to see REST APIs a bit. These HTTP verbs and things that we've talked about, in fact, touch on this. And in fact, the Poke API, and whenever we talk about like getting data from a server, we're talking about a REST API. And it sort of follows these principles. And it can, the sort of formal description of it can get a little nuts, as you can see here. But here we go. This was the bit I wanted to show. The principles are sort of, we have clients and we have servers, and they talk to each other with the protocol. The server doesn't have to do any work if it doesn't get a request from a client. Caching is a little out of scope. we have the same way of talking, and this is really where the HTTP verbs come in, and having all those URLs written the same way, right? The idea being like, I have a course resource and I'm interested in the math class that has ID of 3, and I want to see the students in that class, and in the students in the math class I want to see Bob, who has a student ID of 5, and I want to see Bob's grade. And so we have by using sort of URLs in this way, we have a uniform way to, over the internet, request information, right? And so I can have my JavaScript code send an HTTP request like this, which is exactly what we're going to learn after the break. And I don't have to care about what my Flask server does, if we're using a database, how the database is organized, or any of that, right? All of that is totally abstracted away. And that's getting a little out of scope, but is a great thing to talk about. And as mentioned, we've seen a lot of that. And that's where especially like HTTP verbs and other things come into play. Yeah, great question, Tom. Let's stop here. Let's take a break. Let's take 10. And when we come back, we will actually start writing some JavaScript code to talk to our servers. So thank you guys, and I'll see you all in 10 minutes.